Thank you, Jessica. Okay, now everybody heard that. I am recording now. Thank you, Jessica. Okay, I appreciate that. Looking out for your fellow human beings, or engineers at least. Some of them may be human beings. I'm still admitting people, so that's why I'm distracted by seeing people's names come up and admitting them. All right, let's start with something on the LLN and the CLT. So instead of the mean value theorem, I think what we're going to do is the CLT and the law of large numbers, and then of course within the CLT, the standard error of the mean. So I'm going to switch. I'm going to stop sharing here, and I'm going to go to my handy dandy iPad. Okay, and I'm going to go here, share contents. I'm going to get a whiteboard up. There we go. Maybe. There we go. Good, isn't it? Okay, so what we've got is the difference between the CLT and the LLN. Okay. So if I got a population, okay, some unknown population, and let's say I take a random sample from that. Okay. Okay, taking 5 readings from that population. It could be heights of people. It could be diameters of ball bearings. It could be, how many times professors forget to record special review sessions when they said they were going to record it, right? So any of those things can be a population, right? And we can take different measurements from that population. Now, for a single sample, in this case, we'll have n equals 5, okay? We tend to trust larger samples, okay? Let's just do another one. We'll just call this Y1, Y2, Y3, Y4, Y5, 6, 7, 8, 9, 10, ... Y10, okay? Now, I won't say that Y, sample Y, is necessarily a better sample, okay, necessarily. But if these are taken randomly, okay, if these 2 samples are taken randomly, then we tend to have more confidence, literally more confidence, in the larger sample than the smaller sample. And if, let's say if this sample was, if this population had 1 million, okay? Say there are 1 million times when professors have to record their these sessions, and there's a certain number of a proportion of them that where professors forget to do that, okay? If I took another sample, we'll call it Z, okay? And we'll say n equals 1 million, okay? You would assume that this sample would be a very close approximation to that population, okay? If we do sampling with replacement, it won't be exactly the same as the population, even though it has the same n, because we're taking something out and putting it back in and taking something out and putting it back in. But proportionally, the proportions will be very, 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 very close to the actual population. If we're sampling without replacement, then this sample will be exactly the same as this population, okay? That's what we call the law of large numbers. As the sample size gets larger, okay? As the sample size gets larger, the characteristics of this sample tend to better reflect the characteristics of the population. In particular, the expected value of the sample, the mean of the sample, okay, will tend to reflect the mean of the population as the sample size gets larger. That's the law of large numbers, okay? Okay. Are there any questions about the law of large numbers specifically? This is the one that seems to be most intuitive to people, but I want to make sure.
quick question, Professor
Yeah.
Middleton.
Yeah.
You mentioned the with replacement and without replacement. If it asks for us to define the law of large numbers, would you want us to include that, or is that kind of its own set of definitions?
That's different. Just
Okay.
what I want you to know is that bigger samples on average, okay,
Yep.
on average, are going to be more are going to better reflect the population than smaller samples. That's the law of large numbers in practical speak.
Perfect. Just wanted to ask that. Thank you.
No, good. That's exactly what you should be asking. Thanks for asking for the clarification. All right. So law of large numbers. Now what we're going to do is we're going to try it for the CLT. Okay. Now I'm going to move things around. Sorry, because I've got so many windows open trying to let people in. Let's go to. Let me give it a new whiteboard. Okay. So now again, we're a law of large numbers versus CLT. All right. Now, if I got that population, the central limit theorem says if I take lots and lots of samples, say this is a sample, n equals, I'll say 10, like y, and then I take another sample. I take another sample. These are all simple random samples with replacement. Okay. Dot, dot, dot. In infinity, well, that's not infinity, that's an alpha. Okay, equals 10. If I take infinitely many samples from that population, all of the same sample size, okay, and each of them, this will have a mean, x bar 1, this will be x bar for sample 2, this will be x bar for sample 3, x bar 4, x bar 5, okay? If I take all of these means now, okay, and I examine them and I plot their distribution, their probability distribution, okay, x bar, okay, and this will go from, let's say, negative infinity to infinity. It doesn't have to go from negative infinity to infinity, but it's a continuous random variable along the x-axis. If I plot all of these x bars, okay, the central limit theorem says no matter what the shape of the population, the sampling distribution, the shape of all those sample means will center on the population mean, and this distance right here, okay, between the mean and plus or minus 1 standard deviation, this distance right here is going to be sigma over the square root of n. Okay, this is also, that distance there is also going to be sigma. Check do sigma. Okay, over the square root of n. Okay. So as if I've got a sample size of 10, okay, the width, this width right here will be 1, what's the square root of 10? That's about 3 and a little bit, right? This will be about 1/3 the size of the population. This width right here will be about 1/3 the size of the population sigma. This width right here will be about 1/3 the size of the population sigma. If I took n equals, I'll do one like 100, okay, square root of that is 10, this width will be 1/10 the size of the population sigma. And this distance right here will be 1/10 the size of the population sigma. So as our sample size gets larger, the sampling distribution of the mean gets narrower and narrower, okay? It's about 1/3 the size, isn't it? So if this was, if n equals 10, and this is, and then for the red one, it was n equals 1. So, okay. And if I do n equals 100 in green, that's going to look like this. About 1/10 the size, about like that. Okay. So because of the law of large numbers, each of these samples on average will be better than a sample of 2 or a sample of 1. Okay. And because of that, they'll better estimate the population mean. And because of that, as our sample sizes get larger, they get better and better and better and better And so we get less and less variation in the sample means. And if my sample was, if I had a sample size of 100, okay, excuse me, if I have a sample size of that's infinite, right? Okay, that's what the central limit theorem says, is the limit as n approaches infinity, okay, means that this will be an exact, everything will fall exactly on the population mean. There will be zero error at all, okay? So that is the central limit theorem. Let me put it in another. That's the central limit theorem. The law of large numbers has to do with a single sample and how well the single sample resembles the population characteristics. The central limit theorem deals with a sampling distribution, a collection of, in this case, means, okay? A sampling distribution of the means is a collection of means, okay? And their probabilities arranged in a distribution. And we know that if we've taken those samples randomly from a population, no matter what the shape of the population, that the shape of the sampling distribution will be normal, okay? Will be normally distributed, and the width of that sampling distribution will be equal to the population standard deviation divided by the square root of n. So as n gets larger, as the sample sizes get larger from all those means that we're taking, the sampling distribution gets narrower and narrower. It gets more and more precise, okay? And this is only about precision. It's only about the random error reducing. If we have a systematic error, if each of these is some systematic error, plus one, plus one, plus one, plus one, plus one, all the way to infinity, right? Then our estimate of mu will be mu plus one, right? There'll be some systematic error. We can't fix that. Systematic error, we have to fix with good sampling techniques and good measurement techniques, standardization of those techniques. However, the random error we can get rid of partly, of course, through good precise instruments, but also through taking larger samples. Okay. Any questions about the central limit theorem versus the law of large numbers?
Oh, could you go over how each of them has to do with hypothesis testing?
Sure, yeah. Okay. All right. So the central limit theorem depends on the law of large numbers. If we didn't have this fact that larger sample sizes better reflect, approach the characteristics of the population, right? Then the central limit wouldn't work. So the central limit theorem depends upon the law of large numbers. And so I'm going to focus on the central limit theorem here. So suppose, let's see, in hypothesis testing. Yeah, okay. So suppose I got some population, okay, pop, and suppose that population looks like that. Okay, not normal at all. Kind of a weird S-shaped curve, backward S-shaped curve. Excuse me. And if I look at that, the mean of that's going to be somewhere around here. Okay, it won't be exactly where we would expect 50%, but it'll be somewhere, if the median will be here, and the mean will be somewhere here, this population. If I take random samples from that population, right, I'm going to take a value here and a value here, and they're going to be randomly distributed about the mean, right? And I can take that, and I know that the shape, the long haul shape of all the samples that are taken from that population will have this shape, and not that shape. It'll be shaped as normal. Okay. Got to admit more people. Okay. It'll be shaped as normal. Okay. There we go. And whatever the standard deviation is here, whatever we calculate, this width will be equal to sigma over the square root of n. Okay, sigma, sigma. Okay. All right, now, so let's go with the blue again. If I have n equals, let's say 10, okay? I will have a sampling distribution that looks like that, okay? If I have n equals 100, I'll have a sampling distribution that looks like this, okay? Just gets narrower as this as the square root of n gets larger, all right? Now, so we know exactly what that's going to look like. And so if we think that our sample, okay, taken from that population is a fair representation where X bar is a fair representation of mu, okay, then we can say that center right there, mu of X bar, the mean of all the means that's taken from that population is going to be approximately equal to the mean of our sample. Okay, so we feel really good about our data collection techniques. We feel really good about the precision and accuracy of our measurements and our data. Okay, we don't think we biased it. And so we can, well, if we believe this, okay, if we believe this, then any sample that's randomly taken from this population, okay, we'll call this mu of y, okay, any sample taken from that population, I can compare, I'm going to use a different color. Mu of y is going to be green. No, mu of y is going to be black. Okay. I can take a sample, so y, I'm going to have y bar, okay, and it'll have some sigma. It'll have some, excuse me, some s attached to it. I'm going to take that y bar and I'm going to say, how close is that to mu of x bar? Is it real close right here? Okay, is that distance real close, or is that distance a long ways away? And so hypothesis testing is just saying, is this distance, okay, is this distance between mu of y bar and mu of x bar, is that a big distance or is it a small distance? That's what hypothesis testing is. And because of the central limit theorem, we know exactly what this shape is of the sampling distribution from our population, okay? And so we can determine if this is a good representation of the population of means that could all be taken from that from this population, okay? If this is a good representation of all those x bars, x bar 1, x bar 2, x bar infinity, okay? This is a good representation. Then any other sample, we can determine the probability of any other sample being drawn randomly from that population. And that's what hypothesis testing is. We try to figure out what is that probability. And if that probability is way out in the tail, we say it's unlikely that y bar could have been drawn from that population. And if this sample was closer to the mean, if this mean of this sample is closer to the mean of the sampling distribution, we say it's very likely that we could have gotten y bar at random from the population that x bar is drawn from. Okay. So that is how the central limit theorem impacts hypothesis testing, because we know exactly what the probability distribution is, number one. And we also know that for a decent sample size, it's normally distributed, and we know exactly what the width is, so we can plot this distribution and we can calculate the probability of getting y bar or anything close to it or below it or above it. Okay. Did that make any sense at all? It's the most important idea in all stats, so I'll take the time to do it. But also, it actually is not that easy. Let's see, waiting room. Just a second, I see people coming into the waiting room. Where are we? Waiting room, one person. Okay. What is y bar? That's just a mean I took from that population. Just another mean I took out to distinguish this sample. Could be x bar 2 and x bar 1, like a 2-sample t-test. Did that help, Ethan? It's just another sample mean.
Yeah, so it's just like having another X bar 1, so
Yeah.
like X bar 5 maybe.
Yeah, so I could take this out and I can just call that X bar 2. I can call that X bar 1 is estimating that, right? If I take X bar 2 minus X bar 1, divide it by the, SP square root 1 over square root n, right? That's a t-test. It's that distance. It's just scaled in standard deviation units. Does that help?
Yeah, thank you.
Yeah, cool. Awesome. Beautiful. All right, let's see. What's my next? I got to see what my next, I have to look on my own computer what the next question was. So that was, what does standard error of the mean mean? Okay. So standard error of the mean is the width of the sampling distribution, okay, of all samples, all of the same sample size taken from the same population. It's the width of the sampling distribution, the distribution of means, all taken in the same manner, all with the same sample size, all taken from the same population. So standard error means the error of estimation. The standardized error is Z, it's normal. Standardized error of estimation of all the means taken from a population. That's kind of how you should interpret standard error of the mean. Okay, let's see what my next question is going to be. So I've covered that. Let's do sampling. There was a question that said they want to know, how do you know whether their sample data set is random or has had some sort of systematic thing that's affected the mean, right? I mean, that's kind of what we're doing in the class. That's the the main question. And so, for example, now we'll just do the accuracy precision thing. Okay. 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 So I've got a sampling distribution. I've taken a sample and I'm going to say X bar estimates the mean of the sampling distribution. I think I have a pretty good sample and it's going to be a pretty close estimate of the mean of the population. Okay. Now, if the mean of that population is in fact not well estimated by the sample mean, that means we have some systematic error. We have an accuracy error. Okay. We can have a very precise distribution that the standard error of the mean can be very narrow, right? But we can still have some systematic error between our estimate as indicated by the sample and the population. That's the hardest thing to figure out, whether you have some sort of systematic variation. It could be error in the sense that we just have I haven't calibrated my thermometer, right? Or I've measured it in centigrade or Celsius instead of Fahrenheit, right? So that could cause that sort of a systematic error, right? But it could also be not an error, but it could be variation that we've caused. So for example, if we have I'm gonna make this red again, sorry. If we have a real population that looks like this, right? And this is sigma. If we have a real population that's like that, okay, there's also sigma. And if, let's say this is hardness, okay? No, let's do it. Let's just do hardness. So this is this is a collection of steel, okay? Okay, and this is a standard steel alloy, okay? This is W1, right? Or it's some reasonably hard steel. Now, what I can do is I can quench that steel, okay? I can heat it up to a certain temperature, then I can quench it at a certain rate, and I can make it harder, right? And so all the samples of steel that I could have taken randomly from this population, I took them randomly from this population, and then I hardened them, and then I measure their hardness, and I get a mean, X bar here, okay? that is greater than the population mean, right? The only way that could happen is because it can't happen automatically. I took the sample, okay, and then I annealed it, or I didn't anneal it, I hardened it, right? And so it's the same sample, but I hardened it, and now there's a change in its hardness. The degree to which I've changed that hardness indicates the effect of my treatment. The only way that could have happened is because I have heated up all those pieces of steel and quenched them. And so if I can find a difference here, a significant difference between my sampling distribution and the population distribution, right, a significant distance, then I could say it's really likely that the hardening process that I went through significantly changed the material properties of the original sample. And that's what hypothesis testing is. Okay? That's what hypothesis testing is when I have a sampling distribution that I'm estimating. This is the sampling distribution as estimated by my sample, and I have some population parameter. If that population parameter is probability is out in the tail of the sampling distribution, I can reject the null hypothesis that there's no difference. If it's too close to the mean, then I fail to reject the null hypothesis. Okay. Questions about that? Okay, so if you're on a midterm, and you're going to say, describe why we can use this notion of a distance to help us test hypotheses about the effect of some treatment. Let's see, Ronald says, could we possibly do the step-by-step process on how to explain and use the t-test? We will do that. That's in one of the, that's in the questions we've got right now. That's in the set of questions that we're going to get to. And that's the next one. I just wanted to go kind of in order here. So in fact, most of the questions that came to me were about the Z and T tests. Okay. So let me, let's see, how to determine T and Z scores. Let's talk about those. Okay. Test statistics, all that. All right, let's see. Here we go. Can I explain precision? Yeah, Ethan, precision is just the random variation in a sample, okay, or in a sampling distribution. So we use the standard deviation as a measure of precision. If you have a large standard deviation, then you have low precision. If you have a very small standard deviation, then you have high precision. And of course, precision depends on the context, right? A very precise atomic clock, right? That's very precise, but a stopwatch also has precision. It's not as precise as an atomic clock. Precision is the random variation in a sample. It's the width of the distribution. Accuracy is a displacement of the distribution from some true value. So if you look at this right here, that distance right there is a measure of accuracy, systematic error, and accuracy, okay? This distance right here is a measure of precision. If I took another sample or and that was like this, right? That distance right there is much smaller. This green distribution here is much more precise than the red distribution. Okay, cool. All right, let's do Z-test, T-test, et cetera, et cetera. Okay, so I'm just making sure that we're not leaving anybody in the room here. Okay, good. All right, Z-test, T-test, all that sort of thing. Now, so remember, we got some population. There'll be a green population this time. And it's going to have some mu, right? It's going to have some sigma, right? Let's say the mu is 10, and let's say the sigma is going to be 4. I'm just making it up. Now, suppose we take a sample where n is equal to 9. We're just going to take 9. You see why I'm using 9, because we have standard error to deal with. So let's say n is equal to 9. Okay, so I get a sample size of 9, and I'm going to get some x bar. Okay, I'm going to get some x bar. Let's say x bar is equal to 12. Okay. Now I could have gotten that statistic just due to random chance. It differs a little bit from 10, not even a standard deviation away. So it's not something that's unexpected, right? But with 9, if I take 9 items from that population, okay, then that might be on average a little far away from the mean, given how much the population varies. And so the z and the t-test is something that looks at how far is this away from this. How big is that distance, given how much we expect the population to vary on average. Okay, this is z and t, so z comma t. Okay, and so what we do is we say, I'm going to find out that distance. Oh, let's do it this way. Sorry. I'm going to find out that distance. I'm going to go x bar minus mu. That's the distance between my sample mean and the population mean that we know. Okay, so it's a real distance. But then I'm going to scale it in standard deviation units. So I'm going to sigma over the square root of n, right? So this is going to be z. This is going to be the z distribution. Okay. And all it does is it takes this distance that's in the numerator and puts it into standard deviation units. It makes this sample, the distance in that sample, fit a normal distribution, okay, that's centered on 0, where this is 1, okay, and that's -1. Okay, so okay. And so I can take this and say 12 minus 10 divided by 4 divided by the square root of 9. Okay, that's going to be equal to 2. It's a 4, sorry. Times 3, so that's going to be 6 over 4 equals 1 point. What is that? Is that 6 over 4? Yeah, 1.5. Okay. So we say the distance here is 1.5 sigmas. And 1.5 standard deviation units. And so we say that's 1.5, that's 1 right there. That's 2, so right there. My calculated value of z is 1.5 standard deviations away from what I would expect if everything were random. Yes, Dahlin, in the chat, the z distribution is made up of a bunch of sample means plugged into that equation to make a distribution of z values. Yes, the z distribution is a sampling distribution of the mean, the long haul behavior of infinitely many samples that could have been drawn from that population. Okay, now we're taking one sample. We're saying, if this sample estimates a population mean of this sample, could this have come from this population? And that's how that distance works. How that distance scaled by how much we expect it to vary under the null hypothesis gives us some z value. Okay. Now the question is, what's the, is this far enough in the tail? Yeah, the z-test is part of hypothesis testing, Heather. Yes. Okay. Yes. Okay, so what I have to do is I have to determine how far this is. And then we have to say, is this far enough for me to consider the distance here to be just random, okay? Or whether I consider it to be systematic. Did my annealing or the hardening of those metals work, right? We expect 1.5 sigma if everything is random. It means that this sample that I've taken from the population has no systematic bias. All we have is random error. Okay, so of course there's always going to be some tiny systematic bias, but we're assuming that that's negligible. Okay, and if this is in fact has no systematic bias, and in fact if this is a real difference, then this is far enough in the tail, it's unlikely that that could happen, right? So the null hypothesis is saying the only variation between my two samples is random. There's no systematic variation. But I've found a distance of 1.5 sigmas. Okay, that's a probability of about 90%. Okay, 90% this way and 10% this way. That means only about 1 in 10 times would I ever get a Z that big if I sample from this randomly. And if I believe that a 10% chance is unlikely enough for me to take the bet, right, then I'll reject the null hypothesis and say that my treatment caused that difference. Right? So the assumption of the null hypothesis is always that there's nothing but random variation. There's no true systematic variation between a sample and a population that you're estimating. Andrew is asking a really good question, because this is something that confuses a lot of people. You don't have to do the Z-test, okay, as a calculation here to do the confidence interval. So we'll do the confidence interval right now. Follow up on your question, Andrew. Thank you. So if I want to do the confidence interval, what we're looking at here, let's say, let me do some erasing, okay? Let's get some of the garbage out of the middle. All right, we'll take all that stuff up. Okay. So what I'm going to do now. Okay, I still got the Z distribution so you can see it. Now what we're going to do is I'm going to make this distribution right here, and I'm just going to use, what I'm going to do is I'm going to transform this Z distribution into the same units as the population. So let's say I was doing Rockwell hardness. Okay, so I'm going to transform this distribution here, this green one, into units of Rockwell hardness, not Z units, but Rockwell hardness. And that's what a confidence interval does. So what we're going to do is we're going to say X bar, that's the center of our sampling distribution that we're estimating, plus, or let's do minus, let's do the lower interval first, sorry, minus, okay, Z, now this is critical, at some alpha, okay, times sigma, times sigma over the square root of n, okay, is less than or equal to mu, less than or equal to X bar plus Z sigma over the square root of n, okay? We'll make this alpha over 2, so we'll do a 2-tail test, okay? So what we're saying is I'm gonna determine some area here, alpha over 2 and alpha over 2. And if I find a difference in my means that's big enough to where it falls out in that rejection region, okay, I'm going to consider that, I would consider that to be a significant difference, okay? And you'll notice that this is X bar. So if I make a red distribution here, it's going to translate a little bit. X bar minus Z times sigma over the square root of n. It's going to translate it a little bit, and ours is up this way. So I'm going to translate it here, okay? I'm gonna make it a little further, sorry. Okay, it's gonna translate it. No. There we go, close enough. That's gonna translate it to go right here, okay? I don't know, let's do it. I'll make it 1.5 sigmas. That's what I want to make. Okay. It's going to translate it. So I've got a center of my sampling distribution that's going to be right here, X bar, right? And now I'm going to figure out where is the standard deviation. Okay. So we're going to do Z critical times over the square root of n. This right here, you either look up at a table or use MATLAB or some other calculator. Okay, this is the same value. This is going to be a negative value. This is going to be a positive value. Oh no, what just happened? There we go. Okay, they're going to have a negative value or a positive value. You just take the absolute value of this, subtract it, add it, and this will be from a table or MATLAB. And what's going to happen here is it will plot this is going to be 1.5 standard deviations. Okay, so it's going to look like this. Okay, it's going to make a sampling distribution, okay, where this is sigma over the square root of n, okay, X bar, right? And where this is sigma. Okay. And what we do is we say, where does the mean of our original distribution fall compared to the mean of our sampling distribution? Okay. And so what we're going to do is we're going to, with this Z critical is that value where everything here is alpha over 2 probability. And here, P equals alpha over 2, okay? This is the confidence interval. It's the 1 minus alpha % confidence interval, okay? It's centered on X bar, okay? So it's in Rockwell units. And it'll go to this point right here. It'll go to this point right here. So the lower bound is going to be here. The upper bound is going to be here. And if our population mean falls inside, if mu falls in here, okay, we'll say, well, that's just likely to be random chance. But if mu falls out here, we say, well, we can reject that. We can reject the null hypothesis because our mean is so much greater than the population mean. There is no way to calculate Z critical by hand unless you want to do Taylor series, well, not Taylor series, power series for the normal distribution to integrate it. So you need to look it up in a table or you need to use MATLAB. So Andrew says, does this only work to minimize type 1 error or can something similar be done with beta? So this is great, Andrew. So now notice, see this right here? Okay. This translation and dilation here. Okay, we got a dilation. This is the dilation. What happens is if n is larger, right? The larger the n, the narrower this distribution gets. So I'm going to do it in another color. I'm going to do it in blue. The narrower this sampling distribution gets. And you'll notice now that that probability is very low, okay? And it's much greater for the red, and it's much, much greater, you know, for the green, right? And so if we change n, make n larger, we get more power for the same alpha, because we choose alpha arbitrarily, right? And we can adjust n for a given alpha. We can adjust n to be the lowest n possible to give us that particular cutoff ahead of time. And that's what's called a power analysis. Okay. Will it be our choice on the exam whether you use the test statistic approach? If I ask you, it will be your choice unless I ask you specifically. If I say compute the confidence interval, then you either need to compute it or you need to show me how it's computed. Okay, you don't actually have to compute the confidence interval. We haven't actually done that here, right? But you could show me how it's done and show me the algebra and how you would interpret it, and that's fine. Okay. Does minimizing one type of error increase the chance of the other occurring, or are they independent? They're independent. They're independent. Okay. Because alpha is something that's chosen ahead of time, and beta is dependent upon sample size. So Ryan says, for a problem like this on the midterm, you can explain that equation and how you would use that equation, and that would be sufficient answer on the exam, correct? Yes. Yeah, I speak algebra. You don't necessarily have to calculate it. If you can show me that you understand it and how to make it happen, then the calculation will be done by something else, by a dumb machine. However, if you wish to calculate something or look it up in a table, that is perfectly fine. If that is helpful for you, if that's the way you understand it and know it, that's great. I love that too. So there's no better or worse way to do it. Mateo says, are we going to have to be graphing distribution on the exam, or will charts be provided for us to analyze? You will not have to graph any distributions on the exam. You may draw a picture to illustrate your reasoning, right, by hand or whatever you want to use to draw a picture, but you don't have to graph it. Yeah, for any test, Ethan, the larger the sample, the more power we have, the more we're sensitive to even subtle differences in the sample from the population. Yeah. So what was the question that I missed here? I'm going to look back in. Catherine says, when do we use a z-test or a t-test? All right, we haven't even done the t-test. So we got z versus t. Okay, now this is going to be the one, we're doing the one sample t-test, then I'll do the two, and then the paired sample. But so for the z-test, remember, right? For the t-test, the only difference is whether or not we know sigma versus S. So if we look back at here, if you look here, we know sigma, right? Sigma is equal to 4. So we would use the z-test. I don't have to estimate the population variability. I have it, okay? Now, I'm going to use exactly the same numbers here, 10, 4, 9, and 12, okay? And then we will do the t-test. So let's say we have a population, mu equals 10, okay? But we don't know sigma, okay? We don't know sigma, but we still have a sample that has n equals 9, sorry, and x bar equals 12, okay? But now if I have s equals 4, okay, s equals 4. Now I would use the t-test, and you'll see a little bit. You'll see we'll lose a little bit of power because we're using the t. This will come out exactly the same if s is the same, is a perfect estimate of the sample mean. We're going to get t is equal to 10 minus 12, or sorry, 12 minus 10. I did it the other way last time. 12 minus 10, okay, all over 4 divided by the square root of 9. So that's just going to be 1.5, okay, just like we had last time. I just did the calculation, but the difference is the distribution. In the t-test will look, t-test will look about the same as the z-test. We'll call this t. The z-test, however, will look like this. Okay, so you'll notice, maybe, I notice anyhow, that for a critical value of t, let's say this was minus 1.96, and that is plus 1.96 in z. That means that's going to be 2.5% alpha over 2, and that's going to be 2.5%. Okay, for the t, because it's a little fatter in the tail, okay, the 2.5% is going to be out here. Okay, closer to 2.01. And so you notice, I'm going to use it, maybe notice that distance right there and that distance right there. Okay, you have to have a much larger difference in means, or a larger difference in means, for the t to detect it as a significant difference, if that's the rejection zone, than for the z-test. Okay, that's the only difference. Logically, they're exactly the same. The confidence interval, say 1 minus alpha percent CI, you're going to have t plus or minus t. Use your brain, Jim. There we go. X bar plus or minus t at some degrees of freedom equals n minus 1. Okay, and at some alpha over 2 for a two-tailed test, and we'll get to the 1 versus 2-tailed test in just a second. So this is the critical value. This thing you look up in a table or MATLAB. Okay, and this is going to be S over the square root of n times S over the square root of n, right? So it's exactly the same formula except for that. And the only real difference is you have to use the t distribution because you lose a little bit of precision estimating the population variance instead of using the actual population variation. Okay, let's see what we got here. 11 messages. If you don't know your population standard deviation, the t-test is the go-to. Thank you, Eric. Exactly. Ryan is correct. Boom, boom, boom. Okay, Catherine, we'll get to that. Don't worry. You're about the z-test, binomial hypergeometry, etc. Okay, yes. Angel has got it right. Jasmine worked hard on putting that beautiful flow chart, so you can go right through that flow chart that's on her review video and use it for the midterm. Yeah, that's absolutely a perfect example. Thank you, Angel, for pointing that out to everybody. Okay, so that's the 1 sample Z, 1 sample T. Exactly the same logically. The only difference formula-wise is whether you know the sample, know the population standard deviation, or whether you have to use the sample standard deviation to estimate. Okay, and then you have to use the t distribution because you pay a little bit of a penalty using an estimate instead of the actual parameter. Okay, beautiful, love that. All right, so we've done Z versus T. Now let's do the 2 sample versus a paired sample. That was another question. Okay, so 2 sample T versus paired sample T. Now here is this will be what's on that flow chart, but here's the key. For a 2 sample T test, you need 2 independent samples. If I've got a population, I'm going to take 1 sample, okay, and I'll take another sample. Okay, notice sample 1 does not contain the same values as sample 2. They're independent. They're taken independently from the population. 2 sample t-tests. okay? You calculate X bar 1 and S1, okay? You calculate X bar 2 and S2. And we look at the distance between those two, okay? And then we find this the pooled standard deviation times 1 over N1 plus 1 over N2 to account for the fact that our samples may be of different sample size, T. And degrees of freedom are N1 minus 1 plus N2 minus 1, okay? And so that becomes okay, so I'll do it that way. Easy to remember. So your T is equal to, your two sample T is equal to that value. It's a distance scaled by how much we would, if those two were pulled from the same population, how much we would expect that population to vary. Is what a plus or minus, that's plus, sorry. Thanks, Ryan, appreciate that. Dallin, the assumption is that they are pulled from the same population. Now, sometimes we do an ex post facto study or something where we're looking at males versus females or something, or two different companies. And so then we have to backtrack. We have to say, if they were pulled from the same population, this is what we would expect, right? And so, and then you have to say, well, there's no real difference between these two other than the treatment. And so that's a much harder case to make than if you actually do pull them out of the same population. So that's the difference between an experiment where we randomly sample and randomly assign versus an ex post facto study where we're taking intact groups at the beginning. What is SP? That is the pooled standard deviation. So the pooled variance, is going to be equal to N1 minus 1, S squared 1, plus N2 minus 1, S squared 2. Those are degrees of freedom, times that. And then we do N1 plus N2 minus 2. Okay. If you look at that, if these n's are the same, this is just the average. It's just the average weighted by the sample size. Okay. And if the n's are the same, then it's just S1, S squared 1 plus S squared 2 divided by 2. And so S pooled, the pooled standard deviation, is going to be equal to the square root of S squared, right? Like all standard deviation. Angel asks, bigger the t-score here, the further apart the samples are. Yes. So this is for everything. Bigger the t-score, bigger the z-score, bigger the chi-square, the further apart our sample is from what we would expect under the null hypothesis. Yes. In this case, the bigger the distance between our samples is than what we would expect from the null hypothesis. Under the null hypothesis, we expect no difference. So Angel says, how do we know if it should be x bar 1 minus x bar 2 or x bar 2 minus x bar 1? It doesn't matter. But what you have to remember is if you're doing a one-tailed or a two-tailed, if you're doing a one-tailed test, then it matters because you have to figure out, is good for example, you could say good is stronger, right? I've made my steel stronger. And so that means I would have my experiment. This would be my experimental group, and this would be my control group, okay? However, if I say I want it to be more, I want it to be to use less gas, right? More fuel efficient, less gas, I could do control minus experiment, right? Either of those is fine. Notice all it does, all it does is change the sign of the T. So you have to figure out which tail you're in. That's the only problem with that, Angel. No problem either way. Just remember and draw the picture. Is it the control minus experimental, or is it the experimental minus the control? Okay, draw the picture. Thank you. That's a great question. The t-score is something you look up in a table. No, the t critical value of t you look up in a table. This you actually compute, and you compare this value. You compare that value to t critical at alpha over 2. Okay. You compare those two. And if you have a t distribution, like right here, okay, this is a t distribution. If t calc, this value right here, falls out in the rejection region, okay, then you would reject the null hypothesis. And t critical is that point that demarcates the rejection region right here from the confidence interval here. Okay, this is what this area right here is what I expect under the null hypothesis. This is what I don't expect. This is something that is what I would consider to be less probable than alpha. Okay, and then Jacob says, is that a 2 in the denominator? Is that a 2? That's a 2. Sorry, there's a squiggle. That's a 2. Thanks, Ryan. So the bigger the t-score, the more we prove the alternative. I wouldn't say prove. The more likely it is that the null hypothesis should be rejected. It's all about likelihood. We don't prove anything. We could still be wrong, right? It's probabilities, but it's a bet you should take. What do we compare the calculated t to? You compare it to the critical value of t from a table. So you look up t critical at some alpha over 2, or you compute it using MATLAB, okay, using the functions I gave you for MATLAB in those videos. Catherine. Okay, two-tailed. I haven't gone over this, Catherine, but that's what we're doing next. Can you restate that about prove using statistics? Statistics doesn't prove anything. It only says that there's a likelihood. Remember, proof is exactitude, right? There can be no alterations from the statement if it's proven, right? So we don't prove anything. All we can do is show that it's highly likely or highly unlikely, and we use that to take a bet, right? That's practical. Mathematicians deal with proof. That's impractical. We deal with bets, right? We are gamblers, we engineers. Okay, so a two-tailed test is used just because we want to see whether the samples are different. Yeah, you got it, Tanner. That's the rule of thumb. So we'll show it on the next. We'll do another thing here. So two-tailed test. Okay, remember this is the normal distribution. It could be the t distribution. So what we're going to do is, yes, engineers definitely have gambling problems. You've seen my students. Get rid of that. Okay, so now okay, so this is what I call it an ass from the hole in the ground. This is a two-tailed test. What it says is, I can also say mu1 minus mu2 equals 0. And here I could say mu1 minus mu2 not equal 0. Okay, sorry. All right. So if the samples that are being estimated by two sample t, let's make it mu of x bar 1. Let's make it a sampling distribution. Okay. If these two samples indeed came from the same population, on average, the difference in their means should be equal to 0. That's why the t distribution is centered on 0, okay? Just like the z distribution, okay? And then what I can do is say, I'll accept if the difference is big, right? If the difference is positive and big, or I'll accept it if there's, or I'll say that there's a difference if it's negative with a large magnitude. So what we do is we take our alpha, let's say our alpha is 0.10 here, let's make a big alpha. We're just in the bonehead first stages of an experiment. Then I want to say this is going to be, that distance right there is going to be 0.05, and this is going to be alpha over 2 equals 0.05. And this sum of that under there is going to be 0.05, right? This will be the confidence interval, 90% confidence interval, okay? 90% plus 5% plus 5% is equal to 100%. We've covered everything, right? And so what we do then is we do the t-test, It's an N, sorry. Okay. So we calculate T, and then we look up T critical, okay, for the same alpha over 2, okay. We find T critical, right? Sorry, I put it right there. Okay. We found T critical, that sets that point right there. And we find T critical, and that sets that point right there, the negative value. Okay. Okay. And then and then we could say, where does the calculated value? If the calculated value falls out in the tail here, great, we reject the null hypothesis. If the calculated value falls there, great, we reject the null hypothesis. If, however, the calculated value falls somewhere in between here, that's what we expect under the null hypothesis, right? So what we expect, and so we're going to fail to reject the null hypothesis. That's a two-tailed test. We put half of our alpha in the upper tail and half of our alpha in the lower tail. Let's see. Okay, now we'll do that. We will get to that, Jessica, right after this one. Perfect, we're doing good. Perfect time. Now what we'll do is we'll do a one-tailed test. Okay, assume that's the same shape as the one above. Now what we're going to do is, if we're going to use the same alpha, instead of having alpha right here, instead of having it right there, that's because that's 0.05, right? We're going to put it all the way to here. Okay, so this right here, alpha is equal to 0.10, or we put all of that into one tail. Okay, this is a right tail test. Okay, so what we're going to do is we're going to say the null hypothesis is that, let's do the alternative first. That's how I usually do it. We do mu1, okay, is going to be greater than mu2, and then this is going to be less than or equal to mu2. Okay, right? So what we do then is we do exactly the same thing. It's the same calculation. It's the same distance, same difference, same calculation. But now T critical, instead of being here, has been moved over to here because our alpha now is the full alpha. There's nothing to put in here. Okay. We did not partition it. This is a one-tail test. Shoot. Well, let's see if I can do it. There we go. Close enough. Can't stand that, sorry. Okay. Okay. And so notice there's this distance here between what you would have if alpha is equal to 0.05 t, and this is at alpha equals 0.10. We have all of that area now. So we have more power to detect a difference that might exist if we use a one-tail test. Okay. The bottom distribution is also supposed to be normal. Yes, everything that I draw should look like a normal distribution. Okay. Now, if I wanted to, I could also do it in blue. Instead of the red, I could do exactly the same thing. I could do a left tail test. Uses the same calculation, but now HO is mu1 greater than or equal to mu2. Okay, that's the null hypothesis side. And make the H0. And then H1 is mu1 is less than mu2. Okay. Rejection region corresponds to the alternative hypothesis. The confidence interval corresponds to the null hypothesis. Okay. So we've got, that's the two-tail test. Okay, this right here is the right-tailed one-tail test, and this is the left-tail one-tail test. Same logic for everything. It just depends on where you're putting the critical value, where you're putting your alpha. Are we splitting it into half and putting it in each tail, or are we putting all of our alpha in one of the tails? And if so, which tail? Got it. Just keep that straight. Draw the picture. Write out the null and alternative hypothesis and draw the picture that corresponds to it. Then you won't You won't forget it, you won't mess it up. So, so Trevor says, would the test statistic T in this case be negative? I don't know, let's find out. So here we go. If I've got my T distribution, okay, let's say I've got a one-tailed test and it's going to be in the, this is alpha, right? Right there. This is going to be X bar or set. Oh, this is 0, actually, it's the T distribution. All right. So suppose this this is T crit. Okay. Right. And suppose I have X bar 1 minus X bar 2, sorry, all over SP 1 over N1 plus 1 over N2. Got that, so T calc. Suppose this turns out to be -3. Okay. Now, that's 3 is actually a very large value of T. Okay. That's like 3 standard deviations. That's a standard deviation right there. It's way over here. Right? Oh, excuse me. It's not way over there. It's not there. It's -3. I did that on purpose. It's way over here. Shoot, why is it not T calc -3? Okay, way over here. And this is way in our rejection region, perhaps. Oh, excuse me. Get out of here. Okay. Now, if our rejection region is up here, we have a one-tailed, right-tailed test, and we calculate a negative T value, then we fail to reject the null hypothesis. Okay. It's not in the rejection region. We put all our chickens out in that upper basket. However, if we had done, okay, I'll do it right here, I guess it looks about the same. Okay. If instead of doing an upper tail test, we did a lower tail test and we got the -3, then we would have rejected the null hypothesis. So that's why you got to keep these straight to make sure that you get the correct sign for the tail of the test that you're using. Those are sample 1 and sample 2. Thank you, Yvonne or Ivan. Appreciate that. Does it make sense to use a 2-tailed test when using a 2-sample t-test? Sometimes, Tanner, but only if you have this ask from a hole in the ground. If I know that annealing metal will make it more malleable, right? More ductile, then I should use a 1-tailed test because the direction is clear from the physics, right, from the material science. If, however, I want to know whether men or women prefer a bicycle seat better, or one of them prefers a bicycle seat better than the other, well, how do I know, right? That's when I would use a 2-tailed test. If I don't have physics or some good, scientific theory to back up why it should be better or worse, then I need to use the 2-tailed test. But most engineering examples, you do know what direction it's going. You know why you changed the geometry of that car. You changed it so it would have a better aerodynamic profile. And so you would use a 1-tailed test. Okay. Let me just make sure I'm getting everybody in the chat. Good. All right. Last one's the paired sample. We're doing perfect. Perfect. Paired sample. Remember the 2-sample t-test. Pop. Sample 1. Sample 2. Okay. That's 2-sample t-test. Okay, so let's suppose, do the water blue population. Suppose I took a sample. Okay, and I'm gonna have X1, X2. These are just measurements. There's 4 here. Okay. So I've got my first sample. I'm going to call it pre, and then I'm going to do a pre-test on it. So I'm going to measure. I'm going to measure X1, X2, X3, X4. Right. That's exactly as they come from the population. Then what I'm going to do is I'm going to have a treatment. Okay. And then this is now going to be X1 post. or move this out of the way. Okay. Notice these are paired. Okay, we'll close pre. These are paired. Okay. This was taken from the population. I then measure it and I put some sort of treatment. Okay. Heat treatment, stretching. I can bend it beyond the elastic zone. I can add if all of these are cars and this is brake horsepower, I could put a new transmission in, right? And see if that new transmission gives me more horsepower. But these are not independent. Remember, this is the same car. Okay. This is X1 is the same car, X2 is the same car, X3 is the same car, X4 is the same car. So these values here are dependent upon the initial values. So what do? We'll do X1 post minus X1 pre, X2 post minus X2 pre, X3 post minus X3 pre, and X4 post minus X4 pre. Okay, so we call that D. That's just a difference, right? So if I've improved the brake horsepower, X1 post should be greater than X1 pre. X2 post should be greater than X2 pre. X3 post should be greater than X3 pre, and X4 post should be greater than X4 pre. Okay, and so if I take the mean of the differences, okay, if I take the mean of the differences here, if this is in increasing horsepower, this should be positive, right? It shouldn't be non-zero. And the null hypothesis for this is mu D equals 0. And the alternative hypothesis is mu D not equals 0. Okay, that's a two-tailed test. Or I can do a mu D is greater than 0. That's a one-tailed test, right-tailed test. Okay, right tail. Oops, sorry. Okay. And then we could do a left-tailed test, HO. Sorry, I gotta get my treatments out of here. Shirt. Okay. Okay, so this is two-tail. This is right tail. And this is left tail. Okay, and so what we get is this vector of differences. So I'm going to take away the two sample t-test, since we've already done that. Use this space up here. We got that vector of differences, right? And so T is going to be equal to mu D minus 0. Okay, that's under the null hypothesis, right? And we're going to divide that by SD all over the square root of ND. Okay, so what does this all mean? This is the mean of the differences. Excuse me, not mu, X bar, duh. Just make it there. That's the mean of the differences, okay? And under the null hypothesis, those should be equal to 0 or less than 0, okay? Or greater than 0. It should be 0 or in the other tail. This is the variation of the differences. So that would just be the standard deviation of that vector, okay? And this is the number of those, that vector, okay? Quiz due tomorrow is covering regression. So yes. All right. So the paired sample t-test. Paired sample t-test is just like a one sample t-test exactly the same, where the sample is a single sample taken from a population with a pre-test and a post-test. It's measured once and the same items are measured again, so we can get a vector of differences. So it's not two samples, it's a single sample measured twice. Okay. All right, let's see what my other questions I've got going here. Left tail, right tail, hypothesis test, confidence interval, critical value, test statistic, got all that. Now, for how, what test do I use and when? I could do a quick summary of that, or we can go to, I think we've got power and confidence. So basically now all we have left are what test to use when and regression. So let's do regression, then we'll put it all together. Is that okay? Somebody tell me. Yee, okay. Eric says yee. Okay, now regression. Oof, it's hot in this room with this German wool hat on. It's hot in Germany this time of year. All right, here we go. So regression. Now remember, regression, what we're trying to do is we're asking the question, is there some systematic relationship between two continuous variables? Okay, things that are measured on a ratio or a interval scale. So what we might do is go to, let's do that. I'm going to go and I'm going to share another screen here. Where are we? Share screen. And I'm going to go to the whole desktop. That could be weird. I will get to that. Yes, Catherine. All right. So let's see what I've got here. I want to find the right window. I got too many things going. Admit somebody's coming. Somebody showed up after another class. There we go. Do I want to do force versus displacement of a simple beam? All right. So I've got force in newtons of a simple beam. This is probably spaghetti. I can't remember. And this is the displacement. And you'll notice that these things are actually pretty close to each other with some crazy outliers. All right. Okay. Now, you'll notice that the displacement is not a positive value, it gets negative. It's because I used an electronic distance meter to measure the displacement, and so it goes negative. That's just this, it's how far away is the beam from the electronic distance meter, and it's getting closer by the force, okay? We can do a transformation and put it into where it's positive, so it will look a little more like what you see in material science, but this is basically Hooke's law, right? We've got a straight line, and we could take the slope of that line to look at the spring constant of this simple beam. Now, I have to take a look at this and I have to say, is this real data or not? Just like we did in class in the noon section. If you think this is real data, then you have to account for it in your model. If, however, this looks, what it is the things broke and all kinds of weird stuff happened. So these are outliers, and we should, in fact, first eyeball the data, like in any regression analysis, eyeball the data, and then make a decision about whether we get rid of outliers or not. So what I can do is I'm going to look at let's sort it. And I can do this in MATLAB as well if I wanted to. I'm going to sort I'm going to sort on displacement. Okay. And I get to take the 1, 2, 3, 4, 5, probably the 6 highest displacements. 3, 3, 8. Okay. Sorry, pup. My dog just walked in and he just got neutered today. So yes, I know. So I'm going to take away. I'm just going to take these data points. All right. Now let's see what it looks like. Let's take a look at that. There, we still have a few outliers here. I've got to get rid of the last 2 force data points. Okay, sort. Okay, I have to go up and take a look at it now. All right, close enough. We still got some outliers, but I don't want to keep going on it. Okay. So if you were in Excel, you could we can go to insert. What's a chart element? Wow. Yeah, I can add a chart element. I can go to trend line. I can make it linear. Okay. I could display the equation, display R squared. There. Okay. I've done the regression. I've got a tight fit. I explain about 88% of the variation. My slope is about negative 0.0056 newtons per meter. And we start at about 1/3 of a meter. Okay, easy enough. I want to show you how to do it in MATLAB because it gives you a lot more information, a lot easier. So I'm just going to take my 2 columns of data. All right. I'm going to put them in MATLAB. You don't have to use MATLAB, right? Whatever you want to use. I'm going to put them here. Come on. Why is it not? Did it not copy? Need to copy it and then go to MATLAB. Why is it not? It doesn't. Why? What's going on? More people. One more time. Let's just go like this. I'll just take a bunch of data. Some data. Close enough. Why is it not dropping into MATLAB? MATLAB gone kaput on me. Nope. I don't know what's going on. Well, of course, it's all. Why is it? It just put a shit ton of stuff in the command window as I didn't. Okay, it doesn't like that. Let's go to. Why is it? It's not allowing me to do it. I don't know why we've got this problem here. Okay. Maybe I can do it this way. I got it in the editor here. Take all this. I got too many things open right now, probably. All right, there. Okay, should have done. No, still doesn't. MATLAB import, okay. There we go. So now what I can do is I'm gonna actually take that and see if it'll do it, put it in how you would do it in an exam. Sometimes. Move stuff out of the way, my screen's cluttered. Still won't do it. All right, this is the new version of MATLAB, so. It'll do this. All right. Put MATLAB. Yeah, I'm not a Windows, unfortunately. Yeah, I don't particularly. So I use MATLAB because it's cheap for you guys. Yeah, it's not quick. So something's going on in the background because I've got several other statistical packages going. So I'm gonna do is I'm gonna force quit, and I'm gonna get back in. MATLAB force quit. Yes, I'm forcing you to quit. And then I'm gonna try it again. And I'm gonna just go ahead and get some of this data here. All right, Control C, MATLAB. Yeah, make sure it's working before you go. It was working. It was working before you guys came here. You go home, you put the variable in. Still doesn't do it. It wants to use this new import tool, which I hate. Column vectors, let's do that. Input selection, input. Let's do that. There we go. All right, good. So this is going to be called, come on, got to change the name. Okay, this is going to be force, and it's going to be displacement. Okay, so I've got two vectors, and we can use reg stats. Let's just go up. Those are all the things I pasted. If I have to do this again, I'm going to be really upset. There we go. There we go. So I'm just going to do reg stat, displacement for force. And I use a linear graph. Well, of course. Yes, I can. So I can even do this without having it working right. Displacement is our dependent variable. So that's the first one you list, Aaron. And then force is the independent variable. That's the second. So we regress a dependent variable on an independent variable. And you're used to going in X, Y, direction, right? But it's really Y, comma, X. So let's get out of here. I don't know why MATLAB has changed up on it. Let's see if I can do this. There we go. What we're going to do is I'm going to get the coefficients. I want the fitted values. I want the residuals. I want R square, and I want the T statistic. Okay. All right. So what is just done with this command? I've done a linear regression on displacement and force. It gives me those same parameters. Okay, if we go to Excel, you notice it's the same parameters. 0.363 is the intercept, and negative 0.0056 is the slope. In this case, it's a little different. And that's one of the problems with Excel. It's not going to give you, well, sorry, I only used a subset of the data. So, but it will give you fairly close, but Excel will not give you exactly the same thing as MATLAB, right? So and so this is our intercept, beta 0, and this is our slope, beta 1. So it's a negative slope, and the intercept is about, a third of a meter. Okay. Now I can go back. Okay. I can look at our residuals. Okay. These are all the residual values. These are the errors of estimation. This is how far away the actual points are away from our line of best fit. I can look at R squared. This is not so good because I only use the first few data points, but I'm accounting for about 31% of all the data. Okay. I can use the T-stat. I can say, is this significant? So I can go to T, and I've got a T of the intercept, and a big, huge T, and I've got a T of the slope, and it's negative because the slope is negative. Okay, it's actually a very large T. I can look at that, and I can look at the probability. This is the probability that T that I could have gotten this particular intercept as a function of random chance. Very, very low. So that's the intercept is significantly different from 0. The slope is also significantly different from 0. It has only a 6 in 1,000 chance. If I repeated this experiment infinitely many times, there's only 6 in every 1,000 that would end up with that we could have gotten a slope of that magnitude or greater. Okay, let's see. You can paste the MATLAB code. Yes, you don't need necessarily the analytic formula. You have to explain it though, Joseph, okay? Just have to explain it. I want to know that you understand it. And so if you use the analytic formulas and explain it, you don't have to use the MATLAB. You use the MATLAB and explain it well, you don't have to use the analytic formulas. A lot of people will use both. That's makes it even easier for me, but I want you to show what you know and how you understand it. Yes, Ryan, you could just explain what you would do as opposed to actually doing it. Top number, this is the t-test of the intercept. Is the intercept different from 0? Okay, this, the second number, the 0.0062, is the t-test of the slope. Is the slope significantly different from 0? And the slope tells you, is that relationship between the two variables systematic? In this case, if our alpha is 0.05, this is way below 0.05. Even if it was 0.01, this is way below 0.01. We would consider this to be a significant relationship. It's probably a true linear relationship. Okay. Yes, you could include a screenshot of StatTrack. Yes, no problem. Okay. This is degrees of freedom for the error term, for the t value. Okay. So you notice all of these things are things that you can get very quickly with MATLAB that you would not be able to get easily at all with Excel, although you can. But later on, we'll find out that we'll need even more than this. So that's just running the regression. Now let's take a look back. First thing we did was we eyeballed it, right? Got our data. Let me get this out of the way. And we eyeballed it. Looks pretty good. Then we ran the linear regression. We say, got a good fit. About 88% of all the variation in this data, all the scatter in this data, 88% of it is accounted for by that line, perfect line that runs right through the middle. You'll notice it's a little off kilter because these things are pulling it out of the way. They've rotated it slightly from what I would consider to be the true relationship. But you would say that, right? You could say that in your midterm. Just say, hey, these look like outliers. I'm not going to do that right now, but this would pull it out of the way. And then the thing that Excel doesn't do well, you would, after you finish, do the eyeball, you run your regression, you want to take a look at the t-test of the slope, right? Make sure that it's significant. What we also can do, let me get this out of the way, is we can do a QQ plot of the residuals. Okay. All I'm doing is taking those residuals and I'm going to plot them against the normal distribution and see if they are normally and randomly distributed. And pretty close. This lies really much on the line. There's a little bit of wonkiness in the tails, but very, very little if you look at the magnitude. This lies right on that y = x line. So I would say a linear model is probably appropriate for this data. Okay. Or I could also then do a scatter. Was it displacement? No, it's not displacement. It's force R. I could also then just do a scatter plot of my residuals against the independent variable, and I look at it and I see no distinct pattern. That's pretty random. Okay. So Brent says, why weren't those points that are thrown off the line just thrown out? They would be, but I didn't want to have to spend all the time looking for them and doing it. But that's exactly what you should do. Thank you. Okay, good job. All right, so we've gone through residual. Now, one of the problems you might find is maybe this isn't linear, right? Maybe if we looked at the QQ plot, we'd see some deviation, big deviation, start to say, maybe it's not linear. Maybe these things are not linear and random. Maybe there's some sort of systematic error in our model. And then you would have to take a look at the physics. You'd have to take a look at other things and maybe transform it. So I have another piece of data here. Let's see. No, I don't. I don't have another set of data. But if you wanted to see if a quadratic model would fit, you can just do a simple transformation, right? I can do equals force equals, displacement to the 1/2. We're going to do a quadratic model. If it's a quadratic, I'm going to take its, if I think it's quadratic, I'm going to take its square root. Okay. And you'll notice this is going to be all messed up. I'll draw a picture of it here. Insert scatter plot. And you notice that is not a line, okay? So by taking the square root of it, I've created a bad model. And if I ran the regression on that, we would get a really, you might even get a good fit, but you'd get a really wonky QQ plot, okay? So if I got the data here, force and displacement here, if I then transformed it, I would get something akin to our original model, nice linear model. The QQ plot allows us to see where, if our line of best fit goes through that, let's just plot it. No, we'll just plot a line of best fit. I'm not going to do anything other than plot a linear line through it. Okay. All right. So there's a line of best fit. Notice that it's okay right here, and it's okay right here, but it deviates here, and it deviates here, and it deviates here in the middle. So you're going to see some error. That QQ plot's going to deviate here, here, and here, and be pretty close at these, you know, these kind of cusps where it curves around the line of best fit. So that's how you would read a QQ plot or a residual plot. You start to see curvilinearity in it. You start to see it deviate in particular ways from normal. Get rid of that. Let's see. Will the test be rushed? Some students struggle to finish, and some students finish. You know, I've had students finish in as early as half an hour. I do not recommend that. Okay, just don't recommend it. I recommend you take your time and plan out, and and look at the questions first, and then choose the ones that are going to take more time and plan for it. Take 5 minutes and plan the test out. And that will help you. It is exactly, the questions are very, very, very much like what you've gotten in class, what you've gotten on the practice midterms, what you see in the questions in the book. So there's nothing going to be hidden. If you feel pretty good with the midterms that I posted, then you should be pretty good on this. Okay. Yvonne says, what do we do if it's heteroscedastic? That's a fantastic question. So our original data, I can't go back, dang it, oh well. Don't save. Our original data was let's do this, had some heteroscedasticity, right? And that's where those outliers were. What you could do is you could say, if you believe those outliers are not real data, you can get rid of it. Otherwise, you have to say, my model is not going to be a good model because one of the assumptions of the residuals is that they're linearly and normally distributed. And if I have something that's heteroscedastic, it means that the error is a function of the independent variable, that the error is going to get larger as the independent variable gets larger, or the area or the errors of estimation is going to get larger as the independent variable gets smaller. So heteroscedasticity tells me that there is something systematic in the error. And so a single linear model may not be appropriate. I might have to partition the data into smaller pieces and do smaller linear models piecewise. Okay. That's awesome. Thank you, Iman. Okay, we got 11 minutes left. And I'm still, who was it? Was it Katie that asked about the binomial and all that stuff? Brandon also did as well. Okay, good. Kath, all right. So binomial, I'm going to go back to my other, I'm going to stop sharing here. And let's share here. Somewhere. All right. How do we know when to use these different tests? Okay. So if the outcomes can be classified as a 0 or a 1 only, okay. A 0 or 1 means success, failure, or this, that. Something is either this or that, can't be both, can't be something else, can't be the other, right? It could either be a success or a failure. You can't have a kind of success. Also could be like an animal, not animal, Ford, not Ford. Okay, anything that can be that is a binomial variable, only has 2 values, okay? There are 3 options for you, given what we know now, okay? And these are really the only 3, but you can use a binomial distribution. You can use the hypergeometric. Okay, or you can use Poisson, the fish distribution, okay? Binomial assumes simple random sample. Okay. Simple random sampling. The hypergeometric assumes sampling without replacement from a finite population. Oh, you'll get chi-square, don't worry. We'll get that in just a sec. And the Poisson is theoretically, infinite population, infinite sample. Okay, comma. And then we use what's called an area of opportunity. That area of opportunity is a rate, like hits per second. The number of particles that hit a particle detector in a second, or number of cracks per meter in a cell on an engine, an aircraft engine. What else? It could be the one of the original ones was errors of juries per trial. How many errors in convictions did juries make for a trial? That's actually how the Poisson was developed. As we see, Poisson was studying that. He wanted to ensure fair trials, and he knew that it was less than one. Okay, there was less than one error per trial, but over the course of a year or 5 years or 10 years, there was a fairly large number of errors, even though there was less than one per trial. Right. Anyhow, so these are rates. Okay. That's the hardest part, is to distinguish the Poisson from the others. Binomial, simple random sampling, that means with replacement. Okay. Hypergeometric sampling without replacement from a finite population. And the Poisson has a theoretically infinite sample size. That's why we don't use n in the Poisson in the Poisson formula. We only use mu and e to the x and mu. So mu is the only parameter. Okay. You are being tested on chi-square, and so chi-square, you can have a 0, 1, 2. You can have as many categories as you want, right? But a chi-square, you have 2 variables. Okay, 2 variables, both are categorical. But they don't have to be just 0 or 1. They can be 0, 1, 2. Okay, they can be 0 or 1. But you have 2 variables that you are comparing against each other. The classic example is, I want you to think about a chi-square test just like the 2-sample t-test. It's just like a 2-sample t-test, except, so we'll just do let's do another thing. Chi-square, you can create a contingency table, right? And you have in total, and if you have experimental and control as an example, okay? And this is and those are the treatments. And then we have like successes or failures. Okay, we can let's do this experimental 1, I tried to actually erase that like a whiteboard. Oh no, don't do that. Okay, that's what I'm gonna do. Okay, I'm gonna show you this. So there we go. Okay, it's the samples of steel. The control is just normal samples of steel. Experimental one is at 500 C, okay, and this is going to be at 700 C. We're going to anneal it, okay. We want to look at the successor failures of these through in testing. And let's say we had, oh geez, what just happened? No. There we go. 100 total, okay. And let's say we had 67 successes and 33 failures. And let's say here we had 33, 33, 34. Okay, so not exactly perfect, okay? But you notice this experimental one, that's just a category, right? So that's just like saying 0. Okay, we can label it as a 0. We can label that as a 1 and label it as a 2. Okay, these are just categories. None's better than the other or worse. It's just different. Okay, and that's a 0, 1 thing, 1, 2 thing, Dalin. I just label them. I can label it experimental 1, but I could also code it as 0, 1, or 2. There's just shows that they're different categories. And then we have a success as a 1, let's call it, or a 0. We could also code them like that. It's just this or that. Okay, these are just categories. And so what we can do is we can say, let's say experimental 1 has 17 and 16. Experimental 2 has 22 and 11, right? And then the control has 16 and 17. Does that add up right? Maybe not. 7 and 6, 7, 9 and 6. That doesn't work out. I would have to change my numbers here. That's 33 and 22. That's 55. And so that's 45. That's 30. Yes. No, that's 34. 17 and 16 is 33 and 22 is 55. 16 and 17 is 23. Okay, so I'm missing one. 17 and 16 is 33, 22, 16 and
It's
17.
because your control category, they only add up to 33.
There we go. There we go. So, all right. So let's say this was the data we got. Notice these are just categories for chi-square. Okay. So if I have two, this is like a 2-sample t-test. If I had an experimental and control, this is a 3-sample t-test, right? I got 3 samples and I'm testing them all to see, are these proportions of successes and failures different across these 3 categories? That's what a chi-square test allows you to do. So what I can do is I'll use red, and I could say about 55% of these 33, 55 100ths of these 33 should be here under the null hypothesis if there's no real difference among these categories. So whatever 55% of 33 is going to be, I'll have some expected frequency here. 45%, 45 100ths of 33 should go here. I'll have some expected frequency. And I can then do 55% of 33 for here, 45% of 33 for here, 55% of 16 or 34 for here, and 45% of 100 for here. And you'll notice it looks like there's something going on here. It looks like this category is somehow different than the others. And we could take our chi-square and we could say chi-square is equal to the sum of f, the observed frequencies minus the expected frequencies squared divided by expected frequencies. Okay. Okay. And if the difference between this expected frequency and the observed frequency is very large, it could be negative or positive, that magnitude of this is going to be fairly large, and we square it, it'll make it even larger, okay? And we sum those up, the larger chi-square gets, the further in the tail of the chi-square distribution it's going to be. And we can compare this calculated value against a critical value, okay, that we can look up or have calculated by MATLAB, just like anything else. It's exactly the same logic. It just uses proportions as our estimates as opposed to means. And you'll notice that's just a difference. It's a distance. In this case, we square that distance, and because these are counts, that's actually the standard error, the squared standard error under the in the denominator. So this is just like a squared t-test using categorical data. So I want you to think about these things as the same logically, even though the chi-square distribution has a slightly different shape than the t distribution, that's chi-square. Okay, and the t distribution has a slightly different shape than the z distribution. But the logic is the same. We're looking for bigger differences. Those bigger differences are less likely to be just random differences. They're more likely to be systematic differences. And as engineers, we want to make random differences in our design so that they improve the status quo. Yes, Jake, correct. Do you need degrees of freedom for chi-squared? Yes, Jessica, the degrees of freedom. Here's how you define degrees of freedom. It's the number of rows minus 1 times the number of columns minus 1. Okay, so in ours, we had 3 columns and 2 rows. If I take out 1 column and 1 row, I have 2 degrees of freedom. That would be rows minus 1, 2 minus 1 times 3 minus 1. Okay, so that's gonna be 1 times 2 equals 2. Okay, did that help? All right, you guys have worn me out, but we have gone through every single one of the questions that were posted. And I really appreciate people in the chat and people talking up to keep me going and to correct me as we go along. I hope this has been helpful. It is recorded. It'll take a couple hours for this to be, to get all processed, and I'll have it loaded up for it in all of the sections in module 8, okay, before midnight. All right. Catherine, we just did the difference between hypergeometric binomial and, oh, I just went too far up. Never mind. We're good. Thank you very much for coming. Tomorrow, you've got everything you need. At 12:01, the password will be open for you. Okay. So you'll be able to start taking the exam whenever you're ready. Take your time. Okay. Prepare. And, give me the opportunity to see what you know. Okay, use that as your rule of thumb. All right, we'll talk to you later. Have a great evening. I'm gonna have another beer. Bye-bye.
Thank you, Professor.
No worries. I'm super happy to be here.